So welcome everybody. Welcome to our next workshop in the series of the workshops offered by the Center for AI Innovation. Today we have two presenters, two speakers. They are both graduate students from the University of Illinois, and they both work on graph neural networks. And so that will be their workshop. We will start with Minyang Tian, who will first talk about some of the theory behind graph neural networks. And also then Michael Volk, who is going to give some hands-on demonstrations and tutorials on how to run some of these graph neural networks with some of the libraries that are available in our systems. So with that, please take it from here, Minyang.
So yeah, very glad to be here today to introduce guys the graph neural network, which is a GNN in short, and I hope you can have some basic idea and the intuition about GNN after this talk. So for GNN, first we have to know the definition of graph. What is graph? A graph represents the relations between a collection of entities, and it consists of nodes and edges. And the graphs are actually all around us. Real-world objects are often defined in terms of their connections to other things. A set of objects and the connections between them are naturally expressed as graphs. You're probably already familiar with some types of graph data, for example, the social network and the flight route map and the molecular structure. So in the past few years, with the development of deep learning, GNN have also increased their capabilities and expressive power. So we are starting to see practical applications in areas such as antibacterial discovery and physics simulation, fake news detection, traffic protection, recommendation systems. There's so many applications for GNN. And to study graph, the very first important thing is to transfer natural graphs into a matrix to something like a machine can read. So the goal is to map nodes to d-dimensional embeddings such that similar nodes in the graph are embedded close together. So we want to learn to this mapping function f that takes in the graph and output the positions of individual nodes. So how we can learn this mapping function f? So here we borrow the encoder-decoder structure to illustrate. So our encoder maps each node to a low-dimensional vector. So we have a node in and a d-dimensional embedding out, which is the ZV here. So our similarity function specifies how the relationships in vector space map to the relation in the original network. So similarity in the graph can be viewed as similarity in the embedding space, which is presented by the dot product between the node embeddings. So from this graph, you can see clearly how similarity in the graph can be transformed into similarity in the embedding space. So to further describe the graph for each node, edge, or the entire graph, we can store information in each of these pieces of the graph. And yeah, we can see the GNN training roadmap. So we have the initial encoding of node, edge, and the whole graph based on the nature of your graphs. And then we pass it to GNN to generate some meaningful and expressive output embeddings. And finally, we have task-specific loss and our metric to judge the predictions made by the output embeddings. That's the general training roadmap. We will come back to this plot, I think, several times. Yeah, now we want to further dig into the nature of graph. So as opposed to the fixed neighborhood size of images and text, the number of neighbors to each node is variable. It is hard to phrase in any other way besides a graph. And then adjacent matrix is a very good method to represent the neighborhood relationship in graph. So the elements of the matrix indicate whether pairs of vertices are adjacent or not in the graph. For undirected graphs, the convention is that each edges add 1 to the appropriate cell in the matrix, and each loop adds 2. For example, for the 1 here, you can see it does a loop to itself, so it's 2 here, and it's connected to 2, so it's 1 here. So the expression should be pretty straightforward with these graphs. Okay, I can give an extra example of adjacent matrix, which is a molecular as graph. The molecules are the building blocks of matter and are built of atoms and electrons in 3D space. All particles are interacting, but when a pair of atoms are stuck in a stable distance from each other, we say they share a covalent bond. Different pairs of atoms and bonds have different distances. For example, the single bonds and double bonds. So it's a very convenient and common abstraction to describe this 3D object as a graph, where nodes are atoms and the edges are covalent bonds. So the center one is the adjacency matrix of the bonds in the molecule. And the right one is the graph representation of this molecule. Now that the graph's description is in a matrix format, so we can better describe the graph neural network. So a GNN is an optimizable transformation on all attributes of the graph, which are nodes, edges, and global contexts. And they preserve graph symmetries. I think this is the most important feature of the GNN and why we want to use GNN to solve graph kind of structure problems. So it means our matrix format of graph needs to be permutation invariant. So that will rely on our message passing neural network framework, which I will illustrate later. So here comes a very basic question. Why we need GNN? Can we just use like fully connected or CNN to solve graph problems? Because they are also very powerful. Why we have to invent a new kind of structure to deal with graph? So now I will give you some sense of the reason why graph is hard to learn. So for CNN, RNN, or LSTM, something like that, those kind of modern deep learning tools are mostly designed for simple sequences and grids, which like images. They're simple grids, and the text or speech, they're actually simple sequences. So, but for graph, you will have a way more complex structure. First, it has arbitrary size and complex topological structure, which means it has no spatial locality like grids. So for example, for grids, we can say here's the top left and here's the bottom right, but you cannot say where's the top left or bottom right in graph because it can change its shape easily while still remaining its structure. So there is no fixed node ordering or reference point. That is also the reason why we need permutation invariance for our group representation. The third, it is often dynamic and have multimodal features. So we know that convolutional neural network, or CNN, have been seen to be really powerful in extracting features from images. But as you can see, we cannot directly borrow the sliding window to graph structured data, since you can see sometimes the window contains 3 nodes, and sometimes it contains more nodes. So there's no fixed notion of locality or sliding window on the graph. And the graph is permutation invariant. This makes sliding window cannot work directly on graph. So however, images themselves can be seen as graphs with a very special edition of graphs with a very regular grid-like structure, where the individual pixels are nodes and the RGB channel values that each pixel has the node features. So a natural idea will be consider generalizing our convolutions to arbitrary graphs. So we want to find out a way that GNNs can perform localized convolutions mimicking CNNs. So here comes our message passing framework. So the intuition will be the nodes aggregates information from their neighbors using neural networks. And we can take D as our target node for an example. So for D, we have its neighbors B, C, and E. And B, C, and E also got its neighbors A, C, D, B, D, and D. So we can actually have A, B, C, D, E all have their own computation graph based on its neighborhood. So message passing framework uses a separate multi-layer perceptron. The blocks are all like neural networks. Or you can, it doesn't have to be MLP. You can choose your favorite differentiable models. And we can use separate MLP on each component of a graph. We then call this a GNN layer. So here is the layer 0 actually, with the initial encoding. And here's the layer 1, and here's the layer 2. So for each node vector, we apply the MLP and gets back to a learned node vector. We do the same for each edge, learning a per edge embedding, and also for the global context vector, learning a single embedding for the entire graph. Because a GNN does not update the connectivity of the input graph, we can describe the output graph of a GNN with the same adjacency list and the same number of feature vectors as the input graph. But the output graph has updated the embeddings, since the GNN has updated each of the node, edge, and global context representations. So our model can be of arbitrary depths. We can have arbitrary numbers of layers in our model. And nodes have embedding at each layer. As I mentioned, layer 0 embedding is just the input embedding. And the layer 1 embedding is some aggregation of the information of its neighbors. And the layer K embeddings gets information from the nodes that are K hops away. So there's one thing I want to mention that unlike other deep learning models, GNN is not that if we have deeper models, then we have better performances. We have to choose an appropriate number of layers. We cannot use brute force to infinitely stack layers in GNN, or we will meet some problems. I will explain this by the synchronous message passing graph. So this is our initial receptive field of nodes. When we have deeper and deeper models, it gets the information from its neighbors, and the neighbor of neighbors, its receptive fields are growing. And finally, if this is way too large, which means we stack too many layers, it will encounter the over-smoothing problem. This is bad because we want to use embeddings to differentiate nodes, but not all of the nodes share one embedding. So for receptive field here, I mean the set of nodes that determine the embedding of a node of interest. So when receptive field highly overlaps over two nodes, their embeddings will be highly similar. In a K-layer GNN, each node has a receptive field of K-hop neighborhood. The shared neighbors quickly grows when we increase the number of hops or number of GNN layers. So when we stack many GNN layers, nodes will have highly overlapped receptive fields, and so the embeddings will be highly similar. Then we suffer from the oversmoothing problem. So how to overcome this oversmoothing problem? The rule of thumb, like always number one, be cautious to add any GNN layers. So unlike neural networks in other domains like CNN for image classification, So like I mentioned, so before, adding more GNN layers do not always help. There is also observation from oversmoothing that node embeddings in earlier GNN layers can sometimes better differentiate more nodes. So second is a useful trick or widely used called a skip connection. I suppose like you've been like using it a lot, like if you're have like constructed your own models. So which is just adding shortcuts in GNN to make earlier layer embeddings to be more important. So intuition is that skip connection will create a mixture of shallow GNN models and deep GNN models. So you can see here, we directly add inputs to our output results. So, so far we've talked about the layer connectivity, where we stack layers sequentially and try to add skip connections for deeper models. Now we'll talk about the aggregations. So our basic approach here is to average information from neighbors and apply a neural network. So pulling information from neighboring nodes and edges is a critical step in any reasonably powerful GNN structure. Because each node has a variable number of neighbors, and because we want a differentiable method of aggregating this information, we want to use a smooth aggregation operation that is invariant to node ordering and the number of nodes provided. So for example, for like this target B, so how we put into like the input its neighbors like ACD or DCA or CAD, whatever the order is, they're the same. We have to preserve the permutation invariance. So selecting and designing optimal aggregation operations is an open research topic. A desirable property of an aggregation operation is that similar inputs provide similar aggregated outputs and vice versa. And summary statistics like variance also works. All of these take a variable number of inputs and provide an output that is the same no matter the input ordering. So some very simple candidates permutation invariant operations are sum, min, and max. But there's no operation that is uniformly the best choice. For example, here you can see like for 2, 4, and 4, 4, like for the max, it cannot tell the difference of these, while the min and sum can. And for this part, that max and min cannot tell the difference, but the sum works. So the min operation can be useful when nodes have a highly variable number of neighbors, or you need a normalized view of the features of a local neighborhood. The max operation can be useful when you want to highlight single salient features in local neighborhoods. And sum provides a balance between these two by providing a snapshot of the local distribution of features. But because it's not normalized, can also highlight outliers. In practice, sum is more commonly used. New approaches such as principal neighborhood aggregation, it's taking into account several aggregation operations by concatenating them and adding a scaling function that depends on the degree of connectivity of the entity to aggregates. Now we want to mathematically express the GNN. First, we need to define some notations. Assume we have a graph G, and V is the vertex set, and A is the adjacency matrix. So for the presentation simpleness, I will just assume they're all binary. That's the simplest case. And X is a matrix of node features, and V is a node in V, and the NV is the set of neighbors of V. Okay, so there are three basic parts in our GNN layer. First, the message function. In this step, each node will create a message and send to other nodes later. Second, aggregation. Each node will aggregate the messages from nodes' neighbors. Third, the nonlinearity or activation function, which can add expressiveness. It can be added to the message and aggregation parts. So here it's how it looks in equation. Let me explain. So H is our embedding, and the superscript indicates the layer of the neural net. So at the beginning, initial zeroth layer embeddings are equal to the input node features. So now we are going to create higher order embeddings. So previously we are at level 0, and at level 1 and or higher can be described in this equation. So so here it is the embedding of V at layer L, like which is the previous layer. And here is the average of its neighbor's previous layer embeddings. So we all multiplied them a weight matrix and applied them to the nonlinearity or the activation function. So it can be several steps where, like, to the final layer. Then we have the embeddings after all of our layers of neighborhood aggregation. So here's the output embedding of the node B. So the WL and BL are the trainable weight matrices, or what we want to learn. So WL is the weight matrix for neighbor aggregation, and the BL is the weight matrix for the transforming hidden vector itself. There's one very good property of GNN, is that it's inductive capability. The same aggregation parameters are shared with all neighbors, all nodes computation graphs. We can find that number of model parameters is sublinear, since WL and BL only compare on the embedding dimensionality and the size, not on the size of the graph. So we can generalize our models to unseen nodes based on this. So here are some examples. So if we train the neural network on one graph and apply it on a totally new graph. So since we trained our weighted matrix here, and we can easily transfer it to this neural network. And it's also very useful one for the evolving graph. So we train our GNN here with this graph, and we get the new node. And with the new node, we have the new node's computation graph, and we can just forward the net and generate the embedding for the new node. So this is extremely useful on tasks of social networks. Okay, so general steps of inductive capability is that we define a neighborhood aggregation function. And second, we define a loss function on the embeddings. It can be cross entropy loss or something else based on your task. So then when we train it, we train on a set of nodes or a batch of compute graphs. Then we can generate the node embeddings, and even on some embeddings, we never trained on, since they share the same weight matrices. Okay, now we want to add more tools to our GNN toolbox. So here comes the attention or graph attention network. So the reason why it's called, so it confused me at first, because it should be GAN, right, not GAT. So actually it's because like the generative adversarial network already take that name, so it can also can only be called GAT now. So previously in our GCN network, alpha VU is the weighting factor or importance of the node U's message to node V. So alpha VU is defined explicitly based on the structural properties of the graph or node degree, which means all neighbors U belongs to and V are equally important to node. But we know that's not necessarily the case. So not all the node's neighbors are equally important. So the neural net should devote more computing power on that small but important part of the data. Which part of data is more important depends on the context and it learns through training. So the attention mechanism should focus on the important parts of the input data and phase out the rest. So the goal of GAT is to specify arbitrary importance to different neighbors of each node in the graph. So the idea is that we compute embedding HVL of each node in the graph following an attention strategy. Nodes attend over their neighborhood's message. So by attend, I mean give different importance to them. They're going to implicitly specify in different ways to different nodes in a neighborhood. So we will use byproduct to compute our attention. So let's operation A computes the attention coefficients EVU across pairs of nodes UV based on their messages. So here's the previous layer neighborhood message, and here's the node itself's message. So we pass both of them into our attention mechanism to get the EVU, which can give us the importance of a use message to node V. And here's an example of how it works. So if we want to know how for the node E, how its neighbors contribute to it, it's EED, and of the its neighborhood E and itself D. So then we need a normalization. So for the final attention weights alpha VU, we want to use softmax so that it's add together. When we sum it together, it's total sum is 1. So we just exponentialize the EVU and the over a sum of the exponential, all of the EVK, like sum them over, and we take the weighted sum of them. So here's also a plot like illustrate how we get the final attention weights alpha VU and how it's we get the final output embedding. Okay, so for the form, so what kind of form can we use for the operation A? You're actually free to choose whatever A you want. It just has to be a differentiable model. So here's a common choice where we concatenate them together and apply a linear neural network. And yeah, so that's a common choice. And you can also use multi-head attention, which can stabilize the learning process of attention mechanism. So the idea is that you have multiple attention mechanism A and train them simultaneously. And they're the same, just with different random initializations. Then we have multiple attention scores with different sets of parameters. We can aggregate the outputs by concatenation or summation. So we can often get better performance by considering a general GNN layer design. So design novel GNN layers is still an active research frontier. But these modern deep learning modules can be a good start point. So the first I suggest will be the batch normalization, which can stabilize the neural network training. And the second is the dropout, which can prevent overfitting. It can be added after the batch normalization, and also the attention or gating. mentioned before. You can control the weight or importance of message. And it allows for implicitly specifying different importance values to different neighbors. So here's a common GNN layer setup here. So I think you can, if you want to construct your own layers, you can, if like this one does not work well, it's still a good starting point to make your own edition. So, okay, so we have talked about the message and aggregation in the GNN layer. So we talk about different instantiations under this perspective, and the GCN, the GAT, or graph sage, something like that. You can make construct your own model based on your own choices. So yeah, so now we have the GNN and the output embeddings. Now we come to the predictions. So there are three general types of prediction tasks on graphs: the graph level, the edge level, and the node level. So according to its names, you can know for graph level tasks, we predict a single property for a whole graph. And for edge level, we want to predict the property of edges in a graph. And for node level, we want to predict property for each node. Yeah, so for node level predictions, we can directly make predictions using node embeddings. So after GNN computation, we have the output HV, which is d-dimensional. And suppose we want a k-way prediction. The output head of the given node is some matrix times the embedding. So this matrix can map the embeddings from the d dimension to k dimension to so that we can compute our loss. So for edge level predictions, we can use pairs of node embeddings to make predictions. So there are actually two options we can use. The first will be concatenation plus linear. So here, linear will map the 2D dimensional embeddings. So since we concatenate the embeddings and to a k-dimensional embeddings, because we have like k-way prediction. And the second choice, we can use the dot product. So for one-way prediction, we can directly use the HUL transposed HVL. But for k-way prediction, it's a little bit more complicated. It's similar as the multi-head attention we've talked before. So we have the W1 to WK trainable matrices, and we can concatenate all the results together to have our final results. And for the graph level predictions, we're using all of the node embeddings to make predictions. So it's similar to the aggregation in a GNN layer. So we can use min, max, or sum for our choices. Okay, so yeah, so we have done with the predictions. So we are going to loss functions and evaluation metrics. But I think for GNN's loss function or metric, there's no different than the CNN or fully connected. So for classification, we just use the cross entropy loss. It's a common loss in classification task. So for k-way prediction for ith data points, the equation is here. So the J means the J's class, and I means the ith data point, and the Y is the one hot encoding label, and the Y hat is the prediction after softmax. And if we want the total loss over n training samples, we just sum them together. So yeah, for supervised learning, we can directly train the model for a supervised task without the node classifications. So if it's one-way prediction or the binary classification. So the equation here. So the theta is the classification weight, and the ZV transpose is the node output embeddings, and the YV is the node class label. And for unsupervised learning, so we presume similar nodes have similar embeddings. So the equation is here. As you can see, it's still the cross entropy, where YUV equals 1 when node U and V are similar. The decoder is the similarity function we want to use. Here we just talk about the simplest inner product, but there are also other popular options like random walks, matrix factorizations, and node proximity in the graph. So yeah, for regression task, we can use the mean square error loss, which is also very common. And for the k-way regression for ice data points, it's here. And for the total loss over n training samples, we added them together. And for evaluation matrix, for the classification task, we use when we are having the multi-class classification, we use the accuracy defined here. And for binary class classification, we can use accuracy, precision recall, or ROC AUC. Yeah, actually, for the matrix, I think sklearn should, which is a Python package, should do the job for you, and use accuracy and precision or recall when matrix sensitive to the classification threshold, and if not, just use ROC and AUC. You can actually, if you are not familiar with that, I recommend just in Wikipedia searching for confusion matrix. I think it's clearly stated there. Yeah, and for regression evaluation matrix, you can use root mean squared error and mean absolute error. So yeah, so now we have talked about how do we train a GNN for supervised and unsupervised objectives and node edge graph level objectives. Here are some general empirical tips for training. So at the data pre-processing step, I will say be careful about the node attributes. For example, the probability ranges from 0 to 1, but sometimes the input can have much larger range, say -100 to 100. So be sure to always use normalization before at the data pre-processing step. And the optimizer, I will recommend Atom. It should be robust to learning rate. And activation function, ReLU activation often works well, and you can also try liquid ReLU or something else if ReLU didn't really help at your task. So, and include bias term in every layer to add some expressiveness. And for the embeddings, I will just start with 32, 64, 128, these kind of numbers. I think for more of the experiments issues, I think Michael will talk more about that. So here's just my empirical tips that come right out of my head. And yeah, for the final part of the design space for general GNN framework, I will say the raw inputs is not equal to a computational graph, because it is highly unlikely that the input graph happens to be the optimal computation graph for embeddings. So for example, at a graph feature level, the inputs graph may lack features, so we need to do the feature augmentation. So the common approach will be assign constant values to nodes or one-hot encoding to give unique IDs. At graph structure level, there will be more problems. For example, the graph is too sparse, so which will cause the inefficient message passing. Then we can add virtual nodes or edges to it to solve the problem. And the graph might be too dense. Then we have to use message passing. Then the message passing will be too costly. Then we sample neighbors when doing the message passing. And when the graph is too large, which we cannot fit the computational graph into a GPU, we can sample subgraphs to compute embeddings. Okay, in conclusion, here's the common GNN layer with the linear layer and batch normalization, dropout, activation, attention, final aggregation. And the training roadmap with the initial encoding of the graph, pass it into the GNN, and we have the output node embeddings, and make the predictions, and judge by the evaluation matrix, and iterate with the loss function, I think. We also have outlines some the design space for general GNN framework. We have outlined some of the milestones that researchers have come up with in building neural network-based models that process graphs, and we walked through some of the important design choices that must be made when using these architectures. So here's some references I use and useful links. Any questions?
You have a question in the chat.
Suppose you have a fully connected graph, will the messages be equally passed to each node, in which case classification does not work? Yeah. The messages. If we have a fully connected graph and the messages equally pass to each node, in which case classification does not work. I think it depends on whether the classification will work or not, based on the expressive the dimension of the embedding. Like the dimension of the node embeddings, it has to be sufficient long to have the power of the expressiveness, and the layers cannot be too many. As I mentioned, it will cause the over smoothing problem. Other than that, I think it's the classification task should work well. So if it doesn't work well, I think you can just maybe double the node embeddings and reduce the layers of your GNN. Yeah. Okay.
Can I ask you a question? This was a wonderful presentation. Thank you for the clarity here. A common problem I've heard of is that when you're message passing between nodes that are far away, the message kind of disappears before it's able to propagate multiple hops. Do you know if that's a common problem in practice, or if there are any techniques to avoid that, like adding additional edges to kind of
good question. So first, I don't think that if your graph is really, really large, it might happen, because So, but if you're, because like you can see like for D and B, it got like neighbors of ACD, so it was like exponential growth of the. So our like main concern will be whether it has too many kind of too many layers, but not like whether. But yeah, if the graph is too large, I guess you can actually there's something you can use like called like subgraphs, and you can just take the big graph into pieces, like into maybe 3 subgraph pieces, and each you can bring have a identical GNN network and combine them together later. So there's a way to do that. Yeah, the skip connection will also help. Yes.
And sorry, how do skip connections help? Are they just like new edges being added or something different?
Yeah, just because where's the, yeah, just wait a second. Let me find where the skip connection. Or smoothing, yeah, here. Oh, sorry. Here. So yeah, because why the skip connection will help? Because like if it's just too far away, but when you skip connect to here, like to just after the GNN layer 3, then you are actually passing that kind of far away information into a closer part, right? To your node, to your target node. So the skip connection does not have to be like just 1 layer. It can be like 3 layer or 2 layer, like whatever you want. Yeah, I will say because try first, because subgraph will have some structure, so you have to maybe reorganize the structure. So I will say like try skip connection first, and maybe like skip 3 layers to see whether your kind of the information you want fades away. If it is, then you think about the subgraph issue, and if it works, then yeah, it works. Does that make sense?
Yeah, that's great. Thanks.
Okay, any other questions?
Hi, I had another question.
Yeah.
Typically in the input data, so when I define my vertices, what are the typical dimensions per vertex that I could work with?
Or you mean for the dimension of the...
Just a single vertex, yeah.
A single vertex?
Yeah. What is the order of magnitude that would be typical for a single vertex?
I think like for the embedding length, you can start with 32, perhaps. Mm-hmm. Yeah, that's a common choice, I would say.
Is it possible for different vertices to have different dimensionality?
Is it possible what? Sorry.
For different vertices to have different dimensionality, or would the number of dimensions have to be constant for all vertices?
Yeah, I think you can have the number of embeddings. So why I'm setting it to like 32 and 64 is just like it's easy to like put that into a batch. So yeah, you can use any like length you want.
I think this is the choice. So you're showing the embedding here, the choice that you're going. So the size that you want to embed the features to. but the original dimension of each node has to be the same.
Oh, okay.
I mean, you can impute data, or you can fill, with averages if, say, 10% of the data, or up to say 40% of the data doesn't have values, but they need some value.
Okay. And the dimensionality is typically, so if my embedding dimension is say 32, what can be a possible order of magnitude of my data? So what's a general good range to start out with? Or how much scale down or scale up? Scale down, not scale up, but makes sense.
Do you want me to take this thing in?
Yeah, sure.
Okay. I think that it completely depends on the size of your graph. So the first dimension, if we go back to just one of those message passing framework slides, Minyang, would you mind doing that?
Yeah.
One more with the box. Yeah, if we look at this, so that one. Yeah, so these first nodes at the bottom that are being passed in the shared parameter layer, they have to have a linear layer that is going to be size of that first dimension. So you can reduce the dimension after that first layer, but you're going to have to consider how large that's going to make your model. So your question is, how big should that first node be? Well, as you increase that node dimension, the size of your model is going to get huge.
Okay, so
you can do like you can reduce the features to begin with as a sort of pre-processing step to make your GNN model smaller. Sorry, I cut you off.
That makes sense. So I would essentially be limited by my memory, just my GPU memory. That would kind of determine how big of a model I can have, and then that defines the input capacity.
Yes. Yeah. So the size, ultimately the size, and then it also depends on how big your graph is. How many layers do you need to be able to pass messages, say, K hops away? If the dimension of your graph is huge, you might want to pass messages much further. And Minyang mentioned we usually don't have, with graph neural networks, we usually don't have huge networks anyways, but that might just be, say, an additional layer. So that will also increase your number of parameters. So it depends on the graph. It also depends on how much information you're bringing with each one of the nodes, and also potentially with edges as well.
Okay, thank you.
Okay, so if there's no more questions, I think I will pass the talk to Michael.
Okay, sounds good, Minyang. Thank you very much. Yeah, let's move on to Michael's part.
All right. Hi, everybody. I'm Michael Volk. I'm in the Chemical and Biomolecular Engineering department. I'm a graduate student in Dr. Zhao's lab. And our research related to deep learning in general and graph neural networks in particular has to do with the fact that graphs show up sort of everywhere in biology. So our part of our lab focuses a lot on biology and then also organic synthesis. And so there are a lot of graphs throughout biology and organic synthesis. This example on the left is just showing you molecules. It was already sort of mentioned how molecules can be represented naturally as graphs. We also have interaction networks like the protein interaction network. And we also have disease interactomes. These are sort of more abstracted graphs that are representing things like diseases. There's also some protein interactions here as well. So that's where our interest in graphs come from. And I'll just sort of jump right into it. So the available graph neural network libraries are sort of as follows. There's the PyTorch Geometric. This is what I'm going to be focusing on for the remainder of the talk. There's the Deep Graph Library, DGL. And so I don't really have much description here because I'll be talking about it later, but it's built and based off of PyTorch. And so that's why it's just PyTorch Geometric, but it is an additional package. And then there's DGL, which is framework agnostic. This means that wherever you're coming from, whether you're used to TensorFlow or PyTorch, this might be a good library for you. It's created by distributed machine learning community. And then there's GraphNets. This is DeepMind's GNN library, and it requires TensorFlow. And then there's Spectral. What I found from just their GitHub page is that they're really focusing on just simplicity and quick implementation. So it's based off of TensorFlow, and it sort of follows the simplicity of Keras, which is the high-level API of TensorFlow. And some comments were just that it might be slower than PyTorch Geometric or DGL. And in research, in the literature, it seems that most of the really common, I'm going to disappear this panel, hide control panel. Okay. It seems that in literature, most of the common libraries that are typically used are PyTorch Geometric or DGL. And I just found this table at this link here, and I just updated some of the numbers. And so these are just GitHub stars. So there's a lot of community development for both PyTorch Geometric and DGL, and just as the number of contributors for each one of these libraries. And I just Googled this DGL versus PyTorch Geometric, and this Twitter thread came up. And basically, the differences are sort of in the details. PyTorch Geometric might be fast because of some of the sparse operations that it's able to perform. So if you're really interested in the differences, you'll have to do a little bit of digging and probably also play around with the libraries a bit, testing speeds on different architecture, things like that. So here's PyTorch Geometric, and just the general overview. This is from their GitHub page. So they break things down into sort of these 4 large categories: the engine, which is PyTorch, and then this is really the additional libraries that are brought by Geometric, which are Torch Scatter, Torch Sparse, and Torch Cluster, which allow for some of these fast sparse operations. There's the storage component, which includes data processing, transformation, and loading. And these are just for basically handling graph type data objects. And then we have operators. These include the GNN building blocks and the message passing framework, and then some other typical layers you would see that are specific to graphs, but you would also see them in, say, PyTorch, like pooling and normalization. And then models. And so there's predefined models that you can just use right out of the box. And then there's also user defined models that basically builds off this operators. And predefined models also points to storage, because I believe that you can also load models up with their saved parameters. And so this really includes all of these different packages here. And then I sort of just constructed this little diagram, workflow diagram, to show how these sort of packages interface in a typical workflow that you might use, and when you'll use these different packages along the way. I also included an additional package here that works really nicely with PyTorch Geometric, because there are some functions that allow you to talk back and forth between PyTorch Geometric and NetworkX. And NetworkX is just a package, a Python package, to allow you to do visualization and graph manipulations, and also building graphs. And so you might want to build your graph, say, in NetworkX. This is something that I typically do, and then transform it to a data object with the utility module using, say, from NetworkX. Or you might just want to use one of the existing data sets. This is what we will be doing, using one of the existing data sets for this tutorial. And then from the data, to actually build the model, you will use this Torch NN, and say maybe you'll use a graph convolutional network. And prior to actually bringing the data into the training, you might want to do some transforms. These were mentioned at the end of the last presentation. If you want to do any sort of data manipulation right prior to training. And then you also might want to batch your data. And so this is what the loader is for. You might want to do some sort of special type of loading, especially if your graphs are very large. You might not be able to basically load the entire graph into memory for the training if you say have billions of nodes or something like this. So you might use some cluster loader or some other loader that takes, say, k hops away from a specific node or something like that. And all these interoperate with Torch very nicely. And so this is just going to be the overview. I'm going to talk about the data in some more detail. I'll retouch on the message passing framework as it is specific to the package, PyTorch Geometric. I'll look at a GCN toy example that I built, and then I will do a GCN and a graph attention experiment. And then I'll show you a graph gem in a single experiment and a batch experiment. And then the last slide is just pointing people in other directions for interesting topics. So this is what the geometric data actually looks like. The data object actually looks like. And so it's just this class of data. And by the way, I can't see the chat. So if you guys have questions, you can just sort of unmute and interrupt. I think that'll be fine. So, okay, back to the talk. We have this data object. It's made up of these different arguments here. The two that you absolutely need to construct the graph are x and the edge index. And so x is describing the nodes, the edge index is describing their connectivity, and then optional features include the edge attributes. But if you want to actually run any GCN over these, they say optional, but you actually are going to need these objects to pass messages along edges. So these are the say the node features. So this is what X looks like. So each node has a vector that describes it. This vector can be any dimension depending on the data that you have available to you. It could be, if you don't have any data for your nodes, you can just set, there was a question about this in the chat earlier, you can just set all of these values to 1 if you don't have any data, but you still want to, say, use a GCN and pass messages with the GCN. Or you can apply your data to them. So the way this looks, sort of, this is how it's often depicted pictorially. But the way these look in the actual implementation is these are rotated like this, and this is what your matrix looks like. So it's this size number of nodes, and this is 0th axis, and number of node features. So this is the size or the dimension of the features. And now for the edge index, the way this looks is you have basically pairs of nodes, and it's in this specific connectivity format. And so for an undirected graph, which this is, it has no directionality in the edge, you have pairs. It's basically made directed. So you have a direction pointing from, say, 1 to 0 and also from 0 to 1. So you have this additional entry within your edge index. And so if you're building this graph directly, you're building your own graph and it's directly in PyTorch, you have to make sure that you're doing things like this. You could also use some of the utility functions such as make undirected to account for this type of formatting. Or you can basically directly build your graph in NetworkX, which could be easier, and then just transform. So filling out the rest of this, this is the edge index size of 2 in the 0th axis, and then by the size of the number of edges. And we count 4 edges here because, again, 2 for each of these in either direction. And then the last bit I'm going to touch here is the edge attribute. So the edge attribute takes this shape. So if we have features describing these edges, just data describing the relation there, we basically turn them on their side like this, and it's the size of number of edges. So we have, say, 2 here, and then by the size of number of edge features. Yeah, so the dimension, basically, the length of this feature. Okay. Oh, there is, I guess I can't see the chat. so there's a question about how do you impose directionality when describing the edge index? By making 0 the edge. Yeah, that's exactly right. So directionality, say I want the direction to go from 0 to 1, and it goes 0 to 1, I would get rid of this edge, 1 to 0. I actually don't, so I'm sure this is somewhere in the documentation about how you'd want to do this directly on the data object. I always bring my data objects from NetworkX into PyTorch Geometric. And so I usually bring sort of the full described network from PyTorch, from NetworkX. So if it's directional, I'll bring that network in. And I believe it's when you do the transform, it just automatically eliminates those. And then it's always easier to make something undirected than to make it directed, because you have to specify for each edge if you want to make something directed. But if you want to make it undirected, you're basically doing the same operation over every edge. So this is what the message passing framework looks like from their documentation. So this equation is directly on their docs page. And we have, they basically summarize the different components that you can change based off of these 3 boxes here. So the blue box is the some differentiable permutation invariant function. This is where you're actually aggregating. So this is the, from the previous presentation, it would be this box feature here. The orange is a differentiable function such as an MLP or say just a linear layer. And this is these dashed lines here feeding into the aggregation. And then this gamma green box is a differentiable functions also such as an MLP. All of them are differentiable, so we can actually do a back propagation through the entire network. Okay, so this is the general form. Xi, I is typically considered to be the target node, and J is considered to be in the neighborhood of I. So J in neighborhood of node I. And then EJI is the edge from J to I if you have any edge features. And a lot of applications, especially for the data sets that are supplied, they're not likely to have edge features. So they're less likely, say, than node features typically. And so this is just sort of a summary of how things are defined in terms of the message passing framework. And so they have these different methods to actually define their different functions. So within message passing, you can directly pass the aggregation. And typically there's only a few different types of aggregations used. And that's why you can pass it directly within the arguments. And then there is basically the big function propagate, which is going to internally call message aggregate and update. I'll show this on the next slide with the GCN example. And within the message, this is where we take care of phi. And then within the update, this is where you take care of gamma. And let's see here. Okay. So we won't really deal with gamma for the GCN because there is no gamma essentially. And so we'll focus on the message portion and the propagate portion. And then we'll just look at this keyword argument here. So this is directly from their page on the message passing page. And this is for defining the GCN layer, essentially. So this isn't the entire model. This is just one of the layers. So it would essentially just be the components where these arrows are pointed at. So if you wanted one layer here, you would have, say, one of these classes, class objects. And then if you wanted another one of GCN layers, you would have another class object here. So I'll go through sort of each one of the components. Another nice part of the documentation is they typically report their functions so their update functions in this exact form. Some of them break this this formula, but for the most part, they try to abide by this. So this orange region is the phi function here, and it has a linear layer, and then they also do a normalization. So the normalization just takes the degree of the target node, and the degree is just the number of edges leaving the target node or coming into the number of edges contacting the target node, and the same thing for the neighborhood j. So they normalize every one of the messages by this value, and this is how that is implemented there. So they do the linear transform. Well, okay, let me do step one first. So step one first is they add self loops. So they use this add self loops from the utility functions, utility module, and the addition of self loops is basically this red box that I'm showing here. It's basically adding B into the message passing for adding B or whatever the upstream node is into the message passing. So they do that. And I'm showing this on the computation graph, but you can take care of this by basically just doing a direct manipulation to the data object. And then this will show up automatically in the computation graph. So that's what they're doing there. They then do the linear layer, and then they compute the normalization. So they're just computing this thing. And at the end, they call self-propagate. And propagate does this. It calls message, aggregate, and update. So there's some things going on behind the scenes here. Calls message. So it calls here, and it is applying that normalization then to X. And all of this, since these are basically all in matrix form, every one of these operations is being done simultaneously. So we apply the linear layer to every node at once. And so then we're doing the normalization also to every node at the same time. And so after we've called message, we then call aggregate. And this is also behind the scenes here. See how step 5 is up here. Aggregate is called, we set that keyword argument to add. So then it adds the messages in such a way like this. And then update would be called, but we don't have anything. So all update will do is it will change it'll basically just set the new X value for, I'm going to look at the chat real quick. Why do we want self loops? That's a good question. I think it's, if my memory is correct, I think it's basically so you can continue to contribute the signal, the original signal from that node. And so that so from your target node, that node doesn't just basically transform to its nearest neighbors. It also maintains a strong signal from its original feature vector. But I could be wrong on that. I think that's, like I said, if memory serves, that's the reason. Okay, we'll move on. So now if you want to actually define a layer, you define it in such a way with your in channels and out channels. The in channels is going to be the dimension of your nodes. So there was this question from the last talk, can we have different numbers of node features? So say 2 for node A and 4 for node B. And the reason is no, is because you need to basically have that linear layer have the exact same size for each one of those. And so the dimension, this is basically the dimension of all nodes. So if you're if your graph has 16 dimension for each node, that's why you would set this to 16. And then this is also just on their intro page. Then they're expanding the dimension to 32. And then they're basically doing a forward pass. So they call this layer with their data X and then also the edge index, right? These are the two components you need to pass. And now that's their updated X without any back propagation. So now I'm going to go through a toy example. And I have, for this, and the remaining examples, I have notebooks, but I sort of just cut them down so I can hit the highlights, and we can make those available after if you want to take a look. Okay, so here is just a toy example with some data that I just randomly constructed. So I create a graph with NetworkX. This is the other package that I was telling you about. And it's very easy to do this in this package. And it's also nice for visualization. So I add some nodes, and then I just create some edges. And then I create this attribute called color. And I give it zeros, and one of them is 1. So the zeros, I map them to blue, and the ones I map to orange. So these are the zeros. That's the orange node. And now we're down here. And so I basically, from the utility module, I run this from NetworkX on my graph, and I group the node attributes. So this will group them into the X attribute from data. So I group the color attribute that I assigned to NetworkX, and then we have this data object. So I print the data object, and it looks like this. We have this edge index, and you'll note that we have size or dimension 8 here, and there's 4 edges, but we have 2 for an additional dimension for each edge because it's undirected. And then the size of X is the number of nodes, 4. We have 4 nodes, and then 1 because I gave an attribute for each one of those nodes. And then I just print X. So this is data.x, and it looks exactly like the original attributes that we assigned. And then I print the edge index. This should say data.edge index. Down here, you'll see I didn't put edge index there. So this is data edge index size 8, and you can just see it's describing the connectivity 0 to 1. Say there's 2 to 0. That will be a good one to look at. So there's 2 to 0, and also 0 to 2, but 2 doesn't show up anywhere else. Okay, and then I plotted the features. So I plotted the transposed features of the original graph. So 0, this is just 0, 0, 1, and 0 directly below the nodes. Okay, so now after this, with the conv that we just went over, the convolutional layer, I construct this convolutional layer and its size. So this is from the previous slide. This GCN conv is defined by the input channel, which is the dimension size, and we only have the one attribute, which I called color, so it's going to be size 1, and I expand that dimension to size 3, and then I pass X, and I had to change the type to float because they were originally set as integers, and then I pass the data.edge index, and this is what X actually looks like. So there are 4 nodes, and now after I passed it through, there's an additional 2 dimensions. And so this is with the same sort of visualization technique, this is what these features now look like after being passed through a forward pass of one convolution layer. We could do that again for a second convolution layer. This time we have to match the size, the input channels, to the size of from the previous pass. And so this will be 3 and 3 here. And I just set the same size to 3 as well. And so this is what the features would look like with that same sort of visualization. Now, this is just the forward pass. And so we would do this sort of in our training loop. And then after we do the forward pass, we would compute the loss. And we would then run our optimization scheme, so run our back propagation. And you'll note that we're able to do that because we have the gradients attached to these vectors, to these tensor objects, sorry. Okay, so that's just sort of an introduction about maybe you want to play with some of the layers or build your own layers. And you can sort of look at those objects directly. But now if we actually just want to use some of the pre-existing models, like the GCN that's already implemented, we can just directly import it and then play with some data. So I chose to just look at this core data set. And the core data set is a citation network for some different computing topics and AI topics. Basically what it is if a paper cites another paper, there's an edge constructed, and the labels or the classes of those papers are assigned here. So these are what we're trying to predict. It's a multi-class classification problem on each one of the nodes. And I chose this data set because it feeds into the next example nicely. So we can directly load this from Planetoid. This is part of the Torch Geometrics data sets, like I mentioned. And then this is what the printout looks like. So we have 2,708 nodes, and this is the dimension of those nodes. So the features describing each one of the nodes, the edge index describing their connectivity, and then we have a label for each one of the nodes. You'll note that that's the same size as this. And then we have masks. So a train mask, a validation mask, and a test mask. This allows us to easily just subset portions of the data for training, validation, and testing. And then I went and found, I just printed this list of the classes. So neural networks, case-based, reinforcement learning, probabilistic methods, genetic algorithms, rule learning, and theory. So these are the classes that we're trying to predict based off of this model. This is a visualization of the model. I colored each one of the nodes a different color. And this visualization was done with NetworkX. There's really no great visualization tools within PyTorch Geometric for visualizing graphs. So it's easy just to pass the data back and forth between these two libraries if you want to do any sort of visualization. And I gave each one of the nodes a different color. You can sort of just take away from this immediately that there's a lot of blue nodes. And if you just print out the distribution of the different classes, you'll see that I think there's some nearly 800 blue nodes out of the or maybe 900 blue nodes out of the 2,700. So the classes are a little bit imbalanced. So the first thing I did was I just constructed a GCN and trained this GCN on this network. And this is what that GCN looks like. So these GCN comms are the exact thing layers that we went over previously. And when this model is built, it inherits the neural net.module from PyTorch. And you construct your layers, initialize your layers within the init. And there are two layers here. So GCN comp, it takes the size of the number of features. This is pretty much always true for these GCNs or GNNs in general. And then we pass that to a second layer. And then all of the sort of message passing logic happens in the forward portion. So we get the data from the data object, set that to X and edge index. And then we call the first convolution and we pass it through a nonlinearity. And then we also apply some dropout. And then we pass through the second convolution. And finally, we have the functional logmax of these vectors of each one of the node vectors. So this is just a pretty print of the model itself. And you can see how many trainable parameters there are from each one of the layers. So 23,000 parameters total. And then this is what the train of the GCN looks like. This looks the exact same for the pretty much for any network that you'd be training on this data set. And so I'll just cover this once for the GCN. So you call model.train, and then I just initialize some lists for values that I want to track, like the accuracy and the losses, and I'll plot those later to show you. We zero the gradient on the optimizer. We run the forward pass of the model. We compute the losses, and then we do the back propagation. And that's basically all you need to run say, 1 epoch of this model, and then I basically construct these lists for plotting later. And then for the model evaluation, you basically do a very similar thing. You run the forward pass, and then you just compare that against the ground truth labels. And then I did the exact same thing for the graph attention network. So I'll just briefly introduce that and then show you how that model looks. So this is,
real quick,
yeah, go ahead.
I was so curious, one slide more back, the slide you mentioned the message passing. I'm wondering, where do you specify message passing in here? And like,
Yeah, so
out for something else.
Yeah, so maybe I misspoke. All the message passing actually takes place within the individual layers. So all the message passing takes place in the layer GCN conv. This is where propagate does message aggregation update, message aggregate, and then update if there is an update. So that is happening all right here. So the message passing happens right here for the first layer. Yeah.
Thanks. I was just getting my head around where to specify certain things.
Yeah. And then so what the model is doing is basically combining layers. So it's these are the, after you pass through that first layer, this is the updated feature vectors for X. And then we're going to pass that through another layer, comp2. Now we have updated X again. Okay. Yeah, so this is based off of the just the sort of model formula that I showed earlier on the documentation. And then they post this right above the graph attention network. They updated it to version 2. That's why you see V2, but I just imported this. And this is what it looks like. And so this orange section, and this was discussed previous, so I'll just mention why it looks just a little bit different. There's this linear layer, and this is a part of this phi. And then there's the attention weights. And then you'll see that there's also a linear layer here and another attention over here. These are actually the same thing. The reason they're separated is because this sum is j in the neighborhood of I. And you'll notice that on the convolution, it's j in the neighborhood of I union with I. And so if this was also union with I, we could just basically get rid of that because it would include I over here. This is also could be thought of as adding a self loop. You're including I in the message. So you're including, just for the visual, this is including D in the message means adding this extra pass from D here. Okay. And so to do such a thing, you typically just add self loops directly to the graph. So you manipulate the graph itself. You don't actually add anything additional to the computation. And then there's no gamma for this attention network. And so this is how we actually create the class, graph attention network. Yeah, so I have this first convolution. I just called it conv1 again. And the only additional thing that's added here, so we have input channels, output channels. The only additional thing is heads. And the heads is the number of attention heads. And this was mentioned by Minyang in the previous talk. So you can have multiple attention heads if you so desire, and that will increase the number of parameters for each one of the layers. Everything else is the same. I believe that this block is exactly the same as the previous. And this is what attention looks like. And the only reason I show this is because there's something interesting here, which is that if you want to run this model and you have edge features, you can also include your edge features. And the way that they're incorporated is they're included in the attention coefficient computation. So they're concatenated with xi, xj, and then the edge feature here. this is what the preprint of this model looks like. I just sort of randomly chose these numbers, and so this model happens to be about twice the size with 46,000 parameters. After I run both of these models for 100 epochs, I take these values that I saved from the training, the losses, the accuracies, and I print those. So this is what the losses look like from the convolution and the graph attention. And you'll see that it basically stops learning around, say, 40 epochs or so. Maybe some minimal learning, maybe up in this region. And then these are the accuracy plots. And those also bottom out pretty quick. And then I show the accuracy based off of the test. So this is basically training and validation, and this is accuracy at the very final epoch, last epoch, 100th epoch. I just run the forward pass and compute the accuracy over these 7 classes. And then I just plot them against the random guess. So random guess is just 1/7. That's this first line down here. And then the naive baseline is if you were to take the highest class, since the classes aren't evenly distributed, the naive guess is to basically just always guess the class that shows up the most. So in this graph, that means always guessing the blue nodes. And if you do that, you would get somewhere between 0.2 and 0.4. And so we're doing pretty well with nearly 80% accuracy. And you'll note that the evaluation accuracy for convolution net is better than the graph attention net. So does that mean that the GCN is actually better than the graph attention network? Well, not really, not necessarily so. And we would sort of naively expect the graph attention network to be better. Maybe it has more parameters. Maybe attention is known to be a powerful mechanism. But there are a few things we actually need to do to sort of validate such claims. One of them is we need to repeat runs for model statistics. So what does the standard deviation look like here? And then we need to potentially search over the design space for the best model. And what this means is these numbers that I selected are just sort of randomly chosen. I just necked the size down, and these are things that people do based off of other people's models and based off of some experience. But there's nothing saying that I shouldn't have, say, increased the size here and then dropped the dimension later, or maybe increased more attention heads, or had more attention heads, or maybe even had an additional convolution layer, or maybe had drop out after the last layer. And so I want to test all of those things, but I sort of don't want to build a ton of these models, right? And so there is a part of the PyTorch Geometric Framework. This is a module in the library to actually run these types of experiments, and it's called GraphGym. And it's relatively new. And it's based off of a publication I think I cite in the next slide. And so you can go look at that for more information. But the general idea is that we want to search over the design space to try to find the best model. Once we have the data that we want to test and we have an idea about the types of models and the prediction tasks that we want to do. And so this is the sort of the configuration file that is specified by this YAML file. And this is just from their example. And so I'm going to talk about this portion first, this top half, and then I'll talk about the second half. So this is just where you specify the data that you want to use, the type of task you're doing. So we're doing node classification, whether it's transductive or inductive. That was discussed in the previous talk. The type of split that you want to do, if you want to do any augmentation. And yeah, so there's a couple of different, or transforms, there's a couple of different options here that you have just with the data set alone. And then you also specify where you want the experimental results to go. And then some training parameters. So there's these dimensions here: batch size, evaluation period, and checkpoint period. So how often you save models, how often you evaluate, and how large you want want batches to be. The second portion, which is the bottom half there, is specifying the type of model that you want to use. And so this is just for, right now, we're just talking about a single run. But the nice part about using the configuration file is that you only have to go to the configuration file to change these things, and then you can just rerun your script and it will generate a new experiment with that configuration. You don't have to do any sort of custom parameterization or basically custom configuration or custom arg parse, things like this. So the model is specified here as a GNN, and then within that we specify how this GNN is composed. And this figure here is taken from the design space for graph neural networks that was published in 21. And this is what's included. I think this might even be on the PyTorch Geometric Git page, GitHub page. And so within this, we can specify how layers are connected. And from this paper, they concluded that there's sort of a bread and butter or generic sort of boilerplate that's used to construct GNNs. And that is a pre-processing layer, which are just MLPs, and a post-processing layer, also MLPs. And then you have a message passing layer in between. And then you can also define other things like skip connections within that message passing. And then each one of these individual layers is composed of different components as well, from linear to batch norm to dropout, like we saw, activation like ReLU, and aggregation, different aggregation functions. And so within this GNN, we can specify how we actually want to design our GNN. So we can define the pre-processing layers. So one pre-processing layer, number of layers of message passing. And so that's number of layers here. Number of post message passing layers, number of layers here. The inner dimension, so that's the size that we choose to expand to. So say out channels, something like this. That's what that inner dimension is representing. And then the layer type, so general convolution. You can set this to GAT or something like that as well if you'd like. How you would like to combine these layers. So stack is just what we saw from the previous graph neural networks that I showed. We're just feeding X into the next message passing. You could also use skip connections here, say. Batch normalization or not, activation types, dropout, aggregation, and normalization of adjacency matrix, things like this. You could also add additional options if you so choose. And they have a registration module if you want to do that. And then the last thing is to set the optimizer. So we talked a little bit about the atom optimizer previously, the learning rate, and then the number of epochs to run your experiment. So I ran this experiment, just their single experiment that also uses the core data set for the same prediction task. And this is basically after you have, so I cloned the GitHub repository. And after you do that, you only have to run this run single bash script. And it repeats for 3 runs so we can get our graph statistics. And you just call this YAML file that I previously mentioned. So you're just calling this single file. So say you wanted to run a bunch of different experiments, you can make a bunch of different YAML files if you wanted, or you can, as I'll show in the next slide, use their inbuilt design space to basically generate these automatically. I'll show how that works. So they're grid search. This is what the output looks like from that model that I just showed you. This model has many more parameters, 600,000 parameters, and this is just from the standard output on the terminal. And so we could see that we're recording all the sort of values that we would want to later plot. They, in the development of this graph gem, they made sure that the outputs could be read by TensorBoard. So TensorBoard is often used in conjunction with TensorFlow, but you can just use this separately. You don't need to use TensorFlow. You can download it by itself. And the nice bit about this is after I ran this experiment, it goes to the output directory that I specified from the YAML file, within results and under example. I showed that it had 3 repeat runs, that's 0, 1, and 2. And then the aggregation folder is automatically generated, and that collects a list of the best. So it basically is either one of 0, 1, or 2, whatever the best run was. And this best stats JSON files can then be read by TensorBoard. And so I can just call TensorBoard and then set the log dir to this aggregation directory. And I can just pull up these plots without having to write any sort of custom plot functions like I did for the previous example. And so these are what the plots look like. This is the accuracy. We see the accuracy gets up to, say, 0.84. Okay, so we're already doing better with their toy example than my example, which is great. And the next thing we might want to do is look at sort of a search over many of the different parameters. And this is where we would run a grid search over the different parameters. So this is the a batch of experiments over some grid. And the way we actually run this is we just run this run bash file. And this is what this looks like. And essentially, you can set these values here. So the config, that's what we had discussed previously. It calls that YAML file. And then we also specify this grid file, which is a text file. And for the text file, this is a grid search over the parameter space that we defined. So the way this works is you construct a list of the different parameters that you want to test. And so say for the layers and the message passing, I could set these to 2 and 4, for example, for this experiment. And each line break, it signifies the union over a different grid search space. So this means that the experiment with 2, 2, 2 will run, and also 2, 4, 2 will run, etc. And so with this, I run, so I have 2, 2, 2, 3, and then I also have 2 additional parameters here. And this will give us 8 total experiments. And I specify to stack like I did before, and I set the aggregation. So now when I run this source run batch, I will run these experiments, and I will get an output that looks something like this under the results. It's under this example grid example, and we get the 8 parameter values that I specified from this text file. And so you'll see it has all of those parameters specified just in the file title. So 222, 222, 223. And these first are different types of convolutions, GAT-conv and general conv. And so I could increase this really to however many experiments I want, as long as my computer can handle that, or a cluster can handle that. And then I also include, or they include for you, this aggregation. So it really, it's not much work. They do most of this. They're basically taking care of all the boilerplate for you. And so they give you this aggregation, which gives you the best runs. And within this, this aggregation looks like this. And if I just look at the best epoch CSV, I just converted that to a table, and they rank order them by accuracy, and then second ordering they do by accuracy standard deviation. So you'll see that these two models have the same accuracy, but this one has a better standard deviation. And then we can look at the hyperparameters that were set for that model. So it was 2 layers of pre-processing MLPs, 2 layers of message passing MLPs, and 2 layers of post-processing MLPs. Sorry, message passing graph attention. So this graph attention network was the best model by a slim margin. And then what I can do is I can go back at this portion of the directory, and I can just look for this top model. And I can run TensorBoard on that model, so on that directory. So this is what that directory looks like. It's just basically the description of the run. And I can see plots of those results. And so from these plots, we get somewhere around 0.87 accuracy, which is better than any of my previous runs. And so there are a few caveats, I think, to this whole thing. This is still in active development. And so I didn't really run into any problems, but just from looking around, some people have. And the documentation is still a little bit poor, but it's been improving. There's active commits to the repository, and not all PyTorch geometric functions that are or models that are offered by the base PyTorch geometric are readily available. And so you may have to register them on your own. But this isn't terribly difficult. They sort of give you a couple examples about how you could register custom layers or custom models. And so in the whole sort of experimental workflow, you can think about going from developing your own models to sort of just doing a couple from those models, or say developing your own layers first, doing a couple toy examples with those layers, then applying those layers or building those layers up to construct a model, and then doing a sort of hyperparameter search or a grid search of those hyperparameters with GraphGym. Okay, and then the last thing I wanted to just mention are a few other topics that I think are interesting and piqued my interest, and so maybe they will pique yours as well. There are there's this Open Graph benchmark that is this website that hosts many different graph benchmark data sets. And so if you are building your own layers model and you want to actually test that out, you can download one of these data sets, and they interface with PyTorch Geometric and DGL seamlessly. And so it's only, say, 2 lines of code to, say, download a graph from this and start training your model on it. And they also have some interesting projects, and they also have interesting large-scale projects that are listed here. One of them that I think is interesting to people doing any sort of chemistry is this prediction of the homo-lumo gap problem. And they also have a leaderboard. So once you make predictions, you can post your model to the leaderboard. And that way, the benchmarking and comparison of models is fair and reproducible, et cetera. And then all of these other sections here are models or layers from the PyTorch Geometric Library. The first one here is a model called Attention FP. This is to learn molecular embeddings. They use an attention network. And the cool part about this was that they showed that they can look back at the attention weights. And if they make some sort of adversarial change to a molecule, say they change they change this double bond here to a single bond, they notice that the model is no longer paying as much attention to this ring for its prediction. And so from this, it's not directly, say, causal for explanations, but you can, say, then show this to a chemist, and it can help them, say, generate hypotheses for why a particular prediction is wrong. It basically just helps them use the model in a more investigative way for science. This hypergraph conv is a convolutional layer for hypergraphs, and a hypergraph is distinguished or defined as when a link is shared between multiple nodes. So the links here are these colored blobs. So this purple blob is a link connecting these 4 nodes here. And so the message passing framework is not just limited to sort of vanilla type graphs. There are more complicated message passing type operations that are provided by PyTorch Geometric. This other one here is GNN Explainer. and this is a model that tries to help explain why particular predictions were made. And the last one is this heterogeneous convolution. This is for, again, another sort of different type of graph where you have two distinct types of nodes, one of those nodes being, say, actors, one of them being directors, and another being, say, movies, and dealing with message passing over these different types of nodes. And I believe in the heterogeneous context, you can have nodes with different dimension features. And with that, I'd like to thank you for listening, and I'll take any questions. And then I also had a page of external resources that I really haven't filled out fully, so I can add to that a little bit before I provide the slides. Okay.
Yeah, thank you very much for this, such a sort of practical tutorial on how to do things. Yeah, any questions? I think there is a question somewhere in there.
Yeah, I see it in the chat. Is GraphGym analogous to hyperparameter search? It isn't doing search, and I think I said search many times. It's basically just going over the entire grid. I think they even say grid search. So there was 8 total combinations of the different parameters defining my design space, and it tests every one of those models. Now, I think that you can implement things like early stopping if you decide, or if a model basically just isn't training. And there's another interesting parameter that you could set that is useful for benchmarking, and that is the config budget. So the config budget allows you to constrain the parameter size of the different models. And so the reason for doing this is that often models are compared based off of the total number of parameters that they have. And so, for instance, it's sort of unreasonable to say that in that first example I gave, that the graph attention network performed better than the GCN and it had twice the number of parameters. Well, maybe if I just increase the GCN's parameters to the exact same number, it would perform better. And so it's common to benchmark models with the same number of parameters, and that's the reason you might want to include the config budget. Or if you want to, say, store models on small devices, you might want to prepare for that by setting the config budget to a value where you know that the memory of your device can actually handle.
Any other questions?
Yeah, I could ask another question. This was fantastic. Thank you so much for the details here. In the graph convolution network, I'm curious if you can describe your intuition about input channels and output channels. In what situations would you want them to be the same, or expand or contract when you're going from input to output?
Yeah, sure. Yeah, in what situations? I think that's important. It's pretty situational. If you have, say, no node features, you might want to expand the dimension immediately to try to leverage the expressiveness of the GCN. If you have a very large dimension in the number of features, you might want to drop that dimension to keep the parameter size from getting too large, say, from bloating up your computer or somebody else's computer. So I think that's why it's necessary to basically run experiments over the different parameters. So yeah, my intuition is pretty context dependent. It depends on the type of prediction task also that you're trying to do, and the type of graphs that you're using. But those are I think, the best sort of heuristics, high-level heuristics. If you have no features, you probably want to expand dimension to leverage expressiveness of the model. And if you have a huge number of features, you might even want to do some dimension reduction, or you might want to immediately sort of neck down that dimension to a small number in the out channels to keep the dimensions small. Because if you just keep it the same, and then you have another layer, your 256 squared is huge, right? So if you start with, say, 256 dimension, and you keep it the same right away, your model is already very large. Yeah, thanks for the question. Any other questions? Okay. Well, thank you all for listening.
Yeah, thank you very much, Michael. This is great. So you're going to share with us your PowerPoint presentation or PDF.
Yeah. I'd like to also share. So all of those came from 3 different sort of little mini projects: the toy GCN, the graph attention, and the GCN on Quora, and then the batch experiment. I'd like to share those files with you as well in case people want to reproduce them. So I just need to clean them up. And then I'll send them your way.
Okay, perfect. Sounds good. Yeah, and somebody is asking if this will be posted. Yeah, we will post links to these materials on our ai.ncsi.illinois.edu website. Yeah, this is great. This is really very thoughtful, very nicely done tutorial with so many details about implementation of these models. So thank you very much. I really appreciate you taking time for this. Minyang and Michael, thank you so much. So that concludes today's tutorial.
Thanks.
Thank you.